Hello, everyone. Welcome to the Developing Secure Systems Summit. My name is Nikhil Swami. I'm a researcher at Microsoft Research, and I chair this event, and today I'm going to be the moderator as well. I'm really excited to kick this event off with a talk from Galen Hunt. But before I introduce Galen, let me just take a couple of minutes to provide some context about DS3. You're here, so you've seen some of our communications about the event already. We've had about a bit more than 200 people register for the event so far from about 26 countries. I'm really encouraged by that response. And if you like what you see here, please help spread the word. We have several more talks coming up in the next 5 weeks, and we plan for some more events in the spring. So I think what we're trying to do here with DS3 is to build this community, our community, which I'd like to think is identified by a group of people who really care passionately about computer security. And I think as a group, I hope this resonates with you. We believe that there are principled ways of building systems with security as a core part of their design. As a community, I think we bear a lot of responsibility. The world looks to us to build high assurance computer systems that a digital society can trust. So let's do it. The world's looking to us to make that happen. So I encourage you all to also reflect a bit on what you would want out of an event like DS3. Please let us know right back at that email over there, msrevent@microsoft.com. For myself, I hope DS3 can help connect the dots between research and practice. I'd love to see this grow into a venue where we can share both our successes and challenges, spurring both adoption of current research and also new research to help address problems that are strongly felt in practice. We'll also be reaching out to you to seek your feedback about the event and to gauge your interest in various topics and formats as we schedule more events in the future. Just a couple of words on housekeeping. Stay muted during this call. If you have questions, Teams has a raise your hand feature, and you can raise your hand for questions, and I can unmute you and let you speak at that point. Remember that your audio will be recorded and shared. By participating, you implicitly consent to that. Well, so enough about housekeeping. Let's get to the main event. Let me introduce to you our first speaker, Galen Hunt. Galen works at Microsoft and is a distinguished engineer and founder and managing director of Azure Sphere, a platform to secure the Internet of Things. And you're going to learn a lot more about that from him today. Azure Sphere grew out of work in Galen's team at Microsoft Research, where he worked for at least since the late 90s, I believe. During that time, Galen's led a number of landmark projects, too many to mention, including things like the Singularity Secure Operating System and Drawbridge, a virtualization technology that provides some of the core sandboxing technology used in the Microsoft Azure cloud today. With that, let me hand it over to Galen.
Thank you, Nikhil. All right, I'm ready. Thank you, and it's great to be here. And I see a couple of my Singularity cohorts, companions on the call. It's good to see you. So I appreciate the opportunity to be able to talk to you a little bit about IoT and about security, both in theory and in practice. Let me start off by talking about my journey and where this all began. So about a little over 5 years ago, back in late 2015, somebody walked into my office in Microsoft Research with a floor map of a chip, and it's actually this chip that's on the screen, and said, "Hey, we have this chip that has Could we use this that we've been using in the Xbox hand controllers? Actually, it's about a $2.50 chip, and could we use it for IoT devices?" And I looked at this and realized it was one of these like aha moments in your career. I looked at it and I realized I was looking at the future of computing. I was looking at the next generation of computing. And that's because what is significant about this chip is it was the very first time I had seen a programmable microcontroller and a radio on the same die. and for a price point of just a couple of dollars. So what this chip really meant is that if you had a power source, you had this chip and about 3 or 4 inches of wiring to form an antenna, you could create an internet connected device. And it would be an internet connected device for the price of less than a cup of coffee. And what I realized as I looked at this was everything in the world was going to become connected to the internet. And I went and I started trying to figure out, well, how many MCUs are there out there in the world? That, how many devices is this going to impact? And to give you some numbers, and it all started with this programmable microcontroller. And if you're not familiar with microcontrollers, they are single chip computers. So they've got storage and processor and RAM and I/O all on the same die in a single package. And there are literally billions of devices built on MCUs. There's over 9 billion devices that are powered by an MCU that are built and deployed every year. And it's everything from toys to home appliances to industrial equipment. My test for does something have an MCU in it is if you look at something and it has, it's got electricity and it's got a status light, like a power light, a light that comes on and shows it's on. It has an MCU, unless of course it's got a large color LCD, and then it's got a more capable processor even than that. So they're absolutely everywhere. Okay, and then there's the next kind of question. Well, but would they all become connected? And one of the things I quickly realized as I started to think through this and talk to people is that yes, they would all become connected. And let me give you a really simple example. So think about your refrigerator, and you say, well, my refrigerator's got an MCU in it, but why would I possibly want it to be connected to the internet? What benefit could there be? Well, what I'll tell you is to give you a simple example. So right now, how do you know that the compressor in your refrigerator has gone bad? Okay, well, the way you know, in a COVID-19 world, we're all at home, so we actually probably know while it happens. But that when we go back to where we're not always home, the way you'd know is you'd come home and you'd find like your compressor quit, and so you had melted ice cream and spoiled milk, etc. Right? So the contents are ruined. That's the old way. But in a connected world, the way you'd find out would be you might get a message from your refrigerator manufacturer saying, hey, you may or may not have noticed your fridge making a funny noise, and that's because your compressor is wearing out. And we'll have a truck in your neighborhood this evening with the right part. Could they stop by and replace the compressor in your refrigerator? It'll take about 15 minutes and you won't have the contents of your refrigerator will be just fine. And if we did a raise of hands, my guess is most people want to own that second refrigerator, the new refrigerator, and not the old refrigerator type of refrigerator. Well, one thing I can also tell you is that every single refrigerator manufacturer wants to sell that second refrigerator and not the first one, because the first one, when the compressor goes bad, you have a horrible experience and you don't want anything to do with the good chance you're not going to want to ever buy a refrigerator from that manufacturer again. But with the second one, you fall in love with your refrigerator manufacturer. Wow, these guys are so great. They take care of me. They make sure nothing happens bad to the contents of my fridge. And that's why connectivity is going to hit every single device, because connectivity, and when Microsoft, we use the marketing term of digital transformation. Every industry has become digitally transformed as their devices are able to connect, and that allows them to change the experiences that they produce for the customers. And there's a lot of different additional reasons why you want to add connectivity devices. You can reduce operating costs, eliminating unneeded service calls, for example. You can delight customers, you can streamline your operations, and you can create brand new business models. Like, maybe someone, instead of you have to pay up front for the refrigerator, you pay for milk cooled hours, for example. I don't know what the right business model here is, but connectivity allows you to fundamentally change the business. And so, first core message is the IoT is going to be absolutely pervasive? Yes, it is going to be absolutely pervasive. Every single thing on the planet that can have electricity in it is going to have electricity and is going to be connected to the internet. Just accept it, okay? By the end of the decade, everything's going to be there. And this was a terribly exciting moment for me, because what I realized is, as I looked at that chip, go back to the chip, I looked at it and I realized I was looking at the 5th generation of computing. That this first generation mainframes and then minis, and then micros/PCs, and then phones, and now connected IoT devices. And it was going to be, as each wave has disrupted all the waves before, this wave was going to disrupt all of the other waves as well. So incredibly exciting moment. But then I went through, as we often do, there was the first emotion and then there's a second emotion. And the second emotion I went through was fear. Okay. And that's because, so the person who had come into my office with the chip, the reason they came to me is because I'm the resident OS expert at Microsoft Research. And they were saying, hey, we want to build IoT devices with this chip. What operating system should we put on this chip? And as I looked at the security challenges of this chip, because one of the things about MCUs is they were designed to be air-gapped. They're designed to be these little chips that operate in completely air-gapped, isolated environments where there are no external digital threats. There's no remote threats. And so they have no security built into them at all. They don't have an MMU. They don't have all sorts of things they don't have. And what I realized is if they took this chip and they put it in devices, that as soon as those devices were connected to the internet, any hacker who wanted to was going to be able to come in and own that device. Okay, and you know, I'll just dwell on fear for just a minute. You know, what are some devices that hackers might be able to do something nefarious with based on an MCU? Okay, well, if you have a gas furnace that warms your home, you depend on MCUs to make sure your family doesn't die of carbon monoxide poisoning. Okay, if you have airbags in your car, which you do, those are explosive devices, and you depend on an airbag to make sure that those airbags explode just at the right time, only when the explosion will be counteracted by the forces of an impact, for example. Okay, and on and on and on. You know, you start thinking about, well, what could we do? What could a hacker do? Hackers could do all sorts of amazing damage. You know, basically everything that's controlled in this world is controlled by microcontrollers. Okay, and that, to me, of all, you know, hackers being able to control those devices was a really terrifying thought. And it was that thought that launched a research effort called 4x4 and ultimately became Azure Sphere, because I said, you know, somebody needs to do something about this. We've got to have a more secure options, and somebody's going to have to do something about that. Okay, so again, you know, tremendous opportunity with IoT, but also tremendous risk. But well, okay, just, you know, so one question is, well, just how bad could it get? Just how bad, you know, if we've got all these IoT devices and they aren't really as secure as they ought to be, just how bad can it be? Well, you know, we've all seen headlines. Kind of, you know, the fear-mongering headlines. I mean, but you've seen headlines of things of, you know, fridges being reprogrammed to send spam, and baby monitors being reprogrammed to actually transmit messages into homes, for example, or spying, and on and on and on. There's all sorts of them. One way I describe it is, if you think about the average IoT device that exists today, it should carry an OSHA warning. Okay, so OSHA, the Occupational Safety and Health Administration, you know, they make put warning on like piece of electrical equipment that might have multiple power sources to warn electricians, you know, be careful, you've got this thing really turned off before you do something, and to warn people, you know, that a piece of equipment might start. Well, they really ought to have on IoT devices, probably many of them, and a label that looks like this: insecure device. This device is safe only when used on a secured network. Connecting this device directly to the internet may result in the loss of life or limb. Do not connect to internet. Okay, and that's really kind of where the state of the art was when we got started on this. Give you some kind of very concrete examples. You know, question, well, could you use IoT devices to knock out the internet? Well, yeah, actually you could, and in fact, it's been done. The Mirai botnet attack back in, I think it was November 2016, some hackers reprogrammed the estimates are about 100,000 IoT devices. Ironically enough, most of them were security cameras, and reprogrammed them and turned them into a botnet. Okay, broke into them. And by the way, it was really, really easy to break into them because they all shared the common feature of an admin password that was spelled ROOT. And of course, anybody who's having a Unix, Linux experience knows not the best choice of a password. Okay, even if if you're going to make the mistake of having a common password, having that one was a really bad idea as well. These devices had no early detection. The manufacturers had no idea that the devices had been hacked. They had no remote update ability. So there was, once they had been hacked, or the one, they knew of the hack, they had no way to fix those devices or any other. Huge recalls happened. But anyway, what happened in this attack was they reprogrammed them to launch a distributed denial of service attack against one of the major internet DNS providers for the internet. The net effect of that, it basically knocked the East Coast of the U.S. off the internet for a day. And as I say, that meant, no chat, no video streaming, no online shopping. Frankly, I don't know what anybody on the East Coast did that day. Okay. And imagine, this is 100,000 devices. Let's go back to that billions of IoT devices. Imagine what the internet would look like if there was a distributed denial of service attack launched from billions of devices. And what I'll argue is the internet wouldn't exist anymore. It would be non-functional because they would be everywhere and you wouldn't be able to root them out, and it would be a horrific problem. So something we'd like to not see happen. Another question you might ask, well, could you rob a casino using a thermometer? Okay, and this might sound like the next sequel to Ocean's 11, but this actually happened. One of the casinos in Vegas had a large fish tank, and they had installed. Someone thought, it'd be really great to be able to remotely monitor the temperature of the water of the fish tank to make sure it's okay. And so they bought an IoT device, an internet-connected thermometer, and plugged it into the fish tank and plugged it in their network. Well, that thing had no security whatsoever, and hackers were able to find that device and hack into it. And then they used it as a launch point. They now had a base inside the casino's network, and they were able to explore the network, and they located the high roller database. And if you're a casino, your two most valuable assets are, first, the cash and chips in the safe, and second, the high roller database. Okay, and they located the high roller database. It took significant effort, to break into that database, but they broke into it, and then they extracted it out through the thermometer. I've heard rumor that some of the largest the retail hacks that have happened in terms of stealing credit card databases, one of them came through the HVAC system in that retailer. And the important message here is, often when people think about IoT devices and security is going to add cost to the devices. And they'll say, well, I'm just building a thermometer. It doesn't need security. Or, I'm just building an X or Y, some simple sensor. Why could that possibly need security? It's not going to be able to harm anybody. Well, the problem is IoT devices get put into IoT estates. They get put into IoT systems where there's much more going on around. In this case, it was they used it to attack the database, but they might have used it to kill the fish. Had they got in and fed different data in the sensor and caused the rest of the IoT system that was, say, adjusting the set temperature setting on the fish tank, they could have adjusted that. And so what we see are there's a broad set of class of attacks that can put businesses and organizations at risk. And and we've seen examples of during COVID-19, we've seen a horrific uptake in the number of digital attacks. Both against kind of PC class devices, but also IoT class devices, and we see these devices being bricked or held for ransom, devices that are used for malicious purposes, like, reprogramming the baby monitor, for example, data and IP theft. So using these devices to, steal a high roller database, for example. And we also see this class of attacks of data pollution and compromise. And, if you think about in a world now where ML is becoming very predominant. If you control the sensors, if you're an adversary, and as an adversary, you control the sensors that are being used to build the ML models, well, you control what those ML models contain and what happens in them. And what enterprise wants to know that some adversary is the one that's programming our ML models? Probably nobody. Okay. And then finally, the devices used to attack networks, like the Mariah attacks. We see the whole class of different kind of attacks. And so one of the things you might be asking yourself at this point is, well, are consumers and organizations ignorant of these risks? Probably more ignorant than they should be, more unaware. But what we actually seen, we have a pretty close tap on what's happening. We've actually conducted consumer surveys. We've interacted with enterprise surveys as well. And what we find is actually quite a few people are beginning to have an awareness of the need for more secure devices. Like our data tells us that 65% of consumers say they wouldn't purchase a device from a company that they knew had security breaches, and 74% of consumers say they would be actually willing to pay more for a device if they knew it had more security. We see similar things with enterprises. 97% of enterprises call out security as one of their concerns around adopting IoT. 70% of them would purchase more devices if they knew they were secure, and they'd be willing to pay more for more secure devices as well. And really kind of in both of those two categories, consumers and enterprises, one of the core issues is, but how do I know that a device is more secure? And this is leading into government action. And so we've seen a couple of states pass some what I'll call them is first step laws, around regulations around IoT security. In EU, the upcoming Cybersecurity Act is going to address IoT security. There's the ETSI standard EN 303-645 that we're seeing emerging. It's a baseline for IoT security, and we're seeing it being adopted globally, kind of used as a reference points for IoT security. And it's a good start. I'll put it this way. Do I feel like it's enough for a really secure world? No, I don't, but it's a good start. But, and this is what we're seeing. So we're expecting to see governments starting to issue requirements around IoT security. One of the things we're seeing is labeling standards starting to emerge, where an IoT, a device that can be connected to the internet would have to have a label that says things like, how long is this device supported with updates? Does it automatically update? And some things like that. But kind of the core question is, so what does it take to create a secure device? If I go back to think about that refrigerator example, and you say I'm an OEM, I'm a refrigerator manufacturer, and I want to create a new refrigerator, connected refrigerator. What do I have to know in order to create a secure refrigerator? One of the things I can tell you is most of them have no idea. We spent a good portion of the last 4 years out talking with companies that build MCU-based devices, and their expertise in security is, there's not enough security expertise in the world for every device manufacturer to become an expert on security. And so one of the things we started to do is, we start out actually before we even were building a product per se, we went out and said, well, let's kind of figure out what are the minimum requirements to build a device that you could connect the internet and have some level of confidence that 10 years after that device had been first deployed, when it's still out there connected to the internet, like a refrigerator, for example, that it still is secure. What are the minimums that you have to have? And we identified, and we've published a paper called The 7 Properties of Highly Secure Devices on this. We identified 7 properties that IoT devices need to have. And part of the origin of these 7 devices, we did an empirical study. We went out and looked at every device that Microsoft had built. We looked at every, large classes of devices that our partners had built in the industry, and said, which ones have proven security capabilities, and what are the common properties? Okay, and I'm expecting in this forum all of you to recognize most if not all of these terms. So we identified, you need a hardware rooted trust. You need a hardware rooted trust because unless you can cryptographically validate the identity of the device and secure the boot of the device and things like that, it doesn't matter how much software you put on it, it's still going to be an insecure device. You need defense in depth. You have to assume that devices are going to be hacked. You can't assume, well, I'll just make a tough boundary and nobody will ever get in. You actually have to assume people are going to be able to get into some of your device. And so do you have layers of defense in depth to be able to stop them? You have to have a small trusted computing base. Going back to kind of Butler Lamson's early definition of a TCB, the code that is responsible for security should be isolated from and protected from the code that isn't responsible for security. A good division of labor is a well-founded economic principle. You need to have dynamic compartments. You need to have firewalls within the software and the ability to revise them over time. This is one of the things we've learned from our experience at Microsoft, is that, you know, if you think of it like a 10-year lifetime of a device, on average, about every 5 years, you've discovered a new class of threat emerges that didn't exist before. Like, for example, Spectre and Meltdown, that requires you to make some significant architectural changes in the software of the device. And so you've got to have the capabilities to be able to do that. You need to have passwordless authentication. You need error reporting. You need to be able to know if the devices are not working correctly, if, you know, something's happening. One of the, you know, we built Windows error reporting into Windows almost 20 years ago now. And one of the early things we discovered is, like, we could actually, when hackers were hacking our devices, we got data back. And particularly when an exploit went into the wild, we could get data back. And that could help us figure out what was going on and how to address those, and also how to identify potential vulnerabilities, you know, like bugs, for example, before hackers were able to exploit them. One of the things I tell manufacturers is, if you don't have error reporting in an IoT device, you should just quit, go home, because you just told the world, I don't really care about security if I haven't, you haven't even done the basics. And then the last one is renewable security. The ability for a device to be able to be updated remotely is critical, because new security threats are going to emerge. You're going to identify vulnerabilities that you didn't find initially, and you're going to have new kind of vulnerabilities that become exposed by these new threats. And so you've got to have the ability to be able to update those devices. Okay. Now, one of the things I'll say is every IoT device has to have all 7 of these properties, but and there's 2 ways you can do that. You can either build the property into the device, or sometimes you can add the property outside of the device with human practices and processes. An example of this, like a hardware root of trust. So let's say that your device doesn't have a hardware root of trust. It doesn't have a cryptographically protected embedded identity inside the device. Well, then what you do is you have to ask users to go authenticate those devices. And by the way, this is actually the way PCs work today. If you have an enterprise, you know, you're an enterprise or large organization, you have a PC, the PC doesn't actually have a protected known identity. Okay, what instead is the human has to go log in, and when the human logs in, that is used to, the human's identity is used to bootstrap the PC's identity. So again, you use human practices and processes. Now we've done something about that. Was announced yesterday. I'll come back to that in a minute, but on the PC front. But you know, imagine going back to the IoT devices. You know, imagine having, like, in your home, I anticipate typical home is going to have 100 to a few hundred IoT devices in it. Imagine if you had to every 6 months go log into every single IoT device in your house. That would be a really onerous human practice. Another example is defense in depth. So let's say your device doesn't have defense in depth. That means there's no protection once a hacker is able to get in even to a rudimentary part of that device. And so, for example, you better have a way to contact all your customers if there's a zero-day exploit to tell them to disconnect their devices from the internet really fast before things get really bad. Or let's say you don't have renewable security, so that your devices cannot automatically be updated over the internet. Well, then what that means is you better, if you have an update you got to put up, you're going to have to roll trucks to restore every device by hand. And so you start thinking about these. You know, it's really cheap to not build these into a device, but it becomes really expensive over the long term to add them with human practices and processes. And of course, we recognize that meeting the 7 properties is difficult and costly. And you think about it, there's kind of, I'll break it down into what I call the 3 T's: technology, talent, and tactics. The technology, you know, you think about, so you've got to be able to engineer. So think about this refrigerator manufacturer. They've got to be able to engineer a solution that is end-to-end secure. And they're stitching together disparate components like a hardware root of trust they get from somebody, a TLS stack they get from somebody else, and put them all together. And you've got to do it in a way that's gap-free. It's end-to-end. You know, and we know that security, you're only as good as your weakest link. And so you better not make any mistakes in the components you select or how you put those components together. So that's a pretty high bar. right there. Okay, but let's say, and one thing I've learned, you never go in and tell engineers, I don't think you're up to the task. Okay, so assume that the engineers are going to be willing to invest the time and the energy to be up to task to make a device that's secure when they ship it. Well, the problem is once you ship it, that's when your real problems start, because that's when the device is now connected to the internet. And so you also need to have the talent. You need to have the security talent to be able to recognize and mitigate new emerging threats. So let's say, there's the WPA2, the crack vulnerability in WPA2. You got to be able to figure out, oh, there's this new threat on the horizon. Does it affect my devices? How does it affect my devices? What mitigation do I need to create for my devices? Okay, and that requires a lot of effort and ongoing time and effort. And finally, tactics. You've got to have, so let's say you've got this update for your devices. You have to have the infrastructure, the logistics, and the operational excellence to be able to get that out to all your devices globally, your entire fleet. And in the case of something like a zero-day exploit, you better be able to do it in hours, not days, weeks, or months. And so if you put that all together, that's a really high bar for a device manufacturer. And you ask, is my average refrigerator manufacturer or toy manufacturer or on and on, are they going to be able to do all this? And one of our realizations was we think there's just not enough expertise, and and it's very expensive. It's hard to do this. And this is, well, economics tell you when you have a problem that's really hard and really expensive and requires a great deal of expertise, how can you make a scalable solution, a platform that people might be able to build on top of? And that's what we set out to do with Azure Sphere, and set out on a mission about 5 years ago to build a product. And our goal was to create a platform, and with our mission to empower every organization on the planet to connect and create secured and trustworthy IoT devices. And so, somebody could just use this platform, and if they use the platform, we would take care of security. We would have their back. And Azure Sphere consists of 3 technical components and 1 people/practices component. The 3 technical components are secured chips, a secured operating system that runs on those chips, and a cloud security service that works with the chips to provide them security, keep them secure, and to provide some key capabilities for the interacting with the rest of the world. And then the 4th component is our people, and that is that we actually provide for each Azure Sphere-based device, we provide over 10 years of ongoing security and OS updates. And so, we're the ones that are monitoring new emerging threats, and we see and possible vulnerabilities, and when we identify them, we're going to create the fixes, and we're actually going to update the devices out in the field. So, for example, a refrigerator manufacturer builds on top of Azure Sphere, and let's say a crack, there's a new type of Wi-Fi vulnerability that's disclosed. We're going to actually fix it, and we're actually going to fix the software, the binaries out on their devices for them, so that they don't have to worry about it. And that's what we're trying to do. So let me drill into the details a little bit further. So these chips, Azure Sphere chips, we're not actually getting in the business of building chips ourselves at Microsoft. We're actually working with silicon partners, but each chip has built-in Microsoft security technology to provide dependable hardware-rooted trust. And let me pop into this really quick. So this is kind of a rough architectural diagram of what these chips these Azure Sphere chips look like. And from a secure, so they have the capabilities of a microcontroller, a real-time processor, Cortex-M class processor. They also have a higher level processor, Cortex-A class processor. They have an internet connection and memory and RAM. But the critical components we add is they are secured. So there's a hardware-rooted trust called Pluton, Microsoft Pluton. And if you read the press yesterday, you may have noticed that we actually Microsoft announced that our silicon partners in the PC space, Intel, AMD, and Qualcomm, are all going to now going to incorporate Pluton into their chips. Pluton was actually created in the Xbox One for the Xbox One console. We revised it and made some modifications, particularly for footprint, to incorporate it into Azure Sphere, and we're now getting it into PCs as well. But the idea is that every chip that is based on Azure, that has the Azure Sphere logo, has Pluton in it, so that we've got this very strong hardware-rooted trust that has been proven with over years and years of use in real production. The other, in addition to the Pluton hardware-rooted trust, the chips also have these internal firewalls. Part of Azure Sphere is these internal firewalls that segregate and protect different pieces of the chip. So, for example, if somehow as a hacker is able to get into the NIC on an Azure Sphere chip, they can't get any further. And we also protect the real-time control, for example. So we have a great capability based on this. You can actually come in and debug it. You can debug the high-level processing while the real-time control loop still keeps flowing on these chips. So those are the chips. And the first chips that are commercially available are built by MediaTek. We've got chips coming from NXP and Qualcomm. They both announced publicly that they are producing it. They're in the process of building Azure Sphere chips, and there'll be other names that'll appear over time as well. In fact, the Pluton, the RTL, the hardware-rooted trust, we actually license it royalty-free because we want to really raise the bar of what is available in the hardware-rooted trust. One other comment I'll make here is some people ask, well, is this like a TPM? It's actually, think of it as a TPM++, but it's integrated into the SOC, and that gives us much better security. By having it part of the SOC, it actually can control and monitor what happens with the code on the SOC itself, and that makes a pretty important difference. The second piece, of course, is the operating system that runs on those, and the intent of this operating system is multi-layered defense in depth operating system that creates a trustworthy platform for IoT experiences. So we create a secured software experience. So let's drill into the chips for the operating system for just a minute. Again, it's multi-layered defense in depth. It is based on a custom Linux kernel. So we've taken the Linux kernel and done some optimizations, made some optimizations for it in terms of memory footprint, IoT capabilities, and security. And one of the things you'll notice, it's actually the third layer. Well, if you count from 0, it's the layer 2 in the OS. And one of the impacts of this defense in-depth architecture is that even if our Linux kernel were to get hacked, we still have 2 layers of software underneath that are protecting the device. So with the Pluton runtime, so this is code that runs on the Pluton security processor. Above that, we have the security monitor. Basically, you can think of this as it plays the same role that a hypervisor does in cloud computing. It protects the access to the physical resources. In particular, it protects access to the network and access to storage on the device, so that we can particularly prevent persistent attacks on the device. Then there's the Linux kernel. Our Linux kernel. Above that, we have a set of on-chip cloud services. These provide the implementation of update, authentication, and connectivity and error reporting. And then above that, we have the app layer. So this is where the OEM's code runs. The refrigerator manufacturer's code. And their code runs in containers. And we have 2 kinds of containers or sandboxes. We have real-time sandboxes that run on the Cortex-M. Where they run their real-time control loop, and they're actually over on these separate cores off on the side, but from an OS architecture perspective, they are untrusted code. They are protected, they are isolated, and they are untrusted. And then we have higher level code. So for example, your code that connects to the internet or that interacts with other devices, that runs in a separate class of containers that look very much like a Linux API. Okay. So that's the operating system. Above the operating system, outside the operating, the third component is the security service. And the security service's job is to guard every Azure Sphere-based device. Security, and a key message that we try to explain to manufacturers is security is not a one and done. You have to keep improving your security. You have to keep monitoring, and it's got to be live. And it is the security service that makes security be live for Azure Sphere devices. It does 3 critical things for Azure Sphere devices. The first one is it brokers trust. So for device to cloud and device to device communication is brokered through certificates, and trust is brokered through certificates that are issued by the Azure Sphere Security Service. So we're actually certificate authority for these devices, and basically tell them who they can trust and establish that strong protection there. It also detects emerging security threats through online error reporting and renews device security through update. And we provide update for both our OS, which we are responsible for, and we maintain, we do the updates, and we push the updates out to devices, and a channel for the manufacturers, device manufacturers code as well. So for example, if the refrigerator manufacturer, after the device been out there a while, they say, hey, we'd really like to do an upgrade, sell a new upgrade feature, they can deploy that through Azure Sphere. So they don't have to create any of that infrastructure themselves. And then, of course, the fourth component is the life that we maintain these systems over their lifetime. Now, you might ask, well, how did we go about building in the 7 properties into Azure Sphere? Well, the answer is we tried not to invent anything new that we didn't have to, and we tried to reuse as much experience from across the entire industry that we possibly could, and just took best practices from all over, brought them together, and said, okay, how do we apply them to these very small class of devices and bring them in? There's a full paper here at this URL that you can read if you want to read the details. I think it's about 30 pages now. It keeps getting larger and larger. I'm going to not talk about all 19 of these best practices, but I'm just going to sample a couple of them to give you an idea of how far we go in the security of these devices. So for example, best practice number 5 is using silicon-based measured boot to test remotely the secure boot has completed successfully. Secure boot's fairly well understood principle. You have a base ROM, and the ROM before it loads in the next piece of software, measures the signature, does a measurement of the software, checks the signature matches the measurement, and then loads that piece, and then you bootstrap all the way up through. We've actually gone farther than that. So it's actually implemented in silicon. So for example, our ROM itself is measured by a state machine in the silicon. And as the measurements are put together, when the device goes to talk to the cloud, the cloud security service asks the device, prove to me that you are running the latest version of software. You have all the latest patches. Prove to me that that's what you're running. And that is handed not to like our Pluton runtime or OS. That request actually goes into the silicon, and the Pluton itself it takes that nonce and creates this signs packet saying that we're running the exact right software, and that's actually done in hardware. And that key, that private key, is never accessible to software. So this ensures we get 3 outcomes whenever a device tries to authenticate. We either get a successful attestation saying that the device is running, in fact, the silicon has verified that the device is running the latest software, or we get an attestation that tells the device you have to upgrade and before we'll let you go any further, or we get a failed attestation attempt if somebody's actually manipulated the code on the device. Another example, best practice number 9, make it harder to build botnets out of zero-day vulnerabilities. And so one of the things we've done is we put in network firewalls. We have the silicon firewalls in the bus within the chip, but we also have network firewalls. So with the app, the application has a manifest that says which services it is allowed to talk to. So for example, typically in an IoT device, the app manifest says this device is allowed to call home on this port at this DNS address, and that's all it's allowed to do. And those manifests are published with the application, and the manifest is applied by the operating system. So that if, say, a hacker is able to get into the application and try to reprogram it to turn it into a botnet or to send spam, our firewalls will stop that from happening. And it's just a good best practice that we brought from the industry. And then a last best practice I'll pull in is best practice 15, is really making the software update be fault tolerant. And we do things like we keep last known good images for failback on the machine. We use a separate TCB for update and recovery code. And we use on-device erasure coding to correct local storage corruption. So we can actually, let's say if part of the flash gets erased on a device, we can actually restore that with erasure coding without having to go out to the cloud. And by providing this really robust fault-tolerant update, that provides a really strong base for the manufacturers to build in. And of course, the best practice number 19 is using tools and processes to make software more secure, and we do a lot of things. We do software fuzz testing. We do a bunch of static analysis. We use available tools for analysis on the code. We also use red teams extensively. We do 2 red team exercises on our operating system every year, and we do 2 red team exercises on our cloud service every year. And those red team exercises, Microsoft has some amazing red team hackers. One of the benefits of having a $1 trillion valuation is you can go buy some really, really good people and get them to come in and do red team attacks, and just absolutely amazing what they've been able to do. But we also go out and recruit the best security researchers and hackers we can find out in the world, and invite them to come in and help us. And in fact, we just did the most recent version of this was our 2020 Azure Sphere Security Research Challenge. So over the summer, we did a 3-month security challenge. So we recruited 70 of the most talented individual researchers and security vendors from around the world that we could find. And we offered them bounties and we gave them our code. We gave them dev kits, we gave them our kernel source code, we gave them a direct line to our OS security team, weekly office hours, email support, etc., and said, we're going to give you 3 months, find as many potential vulnerabilities as you possibly can. Okay, and we offered the bounty, the top bounty, if they were able to execute code in the secure world, so inside the security monitor or on Pluton. There was a $100,000 reward for doing that. The results of that were great. We loved it. We actually had 40 submissions from the attackers. 30 of them actually led to improvements that have all been released in our system. 10 of them turned out to be non-issues. We had some issues where they said, "Oh, I was able to break into this piece of code," and we're like, "Well, that's outside the security boundary. That's inside your code." There were some things like that. We actually handed out almost $374,000 of bounties. The largest bounty we paid out was $48,000. The smallest was $3,300. And we had some really great results. I will say McAfee and the Cisco Talos teams were absolutely fantastic. They found a lot of potential vulnerabilities, including a zero-day exploit in the Linux kernel that we worked with Linus and crew to get that fixed and addressed in core Linux. And so we're contributing back. Our bounties are contributing back to the overall community as well. And one thing I'll point out, even though they were able to get kernel root access and through some nefarious ways, they weren't able to get into the secure world. They weren't able to get into Pluton, which meant we still retained. They were not able to create a persistent attack on the device, and we were able to reclaim those devices. And even with those issues that were addressed, and we mitigated them. We had fixes for every single issue in less than a week, and all of the issues, for most of them, a few of them took a little bit longer, including the Linux kernel update to get that out publicly. But all of those have been fixed in our software. More importantly, every single Azure Sphere-based device has been fixed to address these potential vulnerabilities because of our ongoing security updates. I'll just kind of briefly touch on the kind of depth that McAfee went through, because it really demonstrates what real hackers are willing to do. They really became experts in our product. They analyzed every single piece of publicly available documentation we had. They watched every YouTube video we have. They used tools to reverse engineer our binaries, the ones that they didn't have source code to, and they split up into multiple teams attacking different parts of the software. They attacked every single possible surface, everything from drivers, the Wi-Fi code, network stack, etc. They went as deep as possible, and they built rogue applications. We gave them devices that they could run applications on, and they specifically went after building rogue applications, which would be, if you think about if someone's able to find a vulnerability into your app and reprogram the app, then effectively they get that same kind of access. So really, really thorough job. And I think if I remember correctly, they were the ones identified the most potential vulnerabilities in our system. Okay. I want to kind of tie this back up. So we think about IoT. there is amazing opportunity for IoT. IoT is I should have pulled in a slide on this, but I'll give you an example. One of the companies, our first companies that we worked with that has deployed Azure Sphere is Starbucks. And Starbucks is using Azure Sphere to protect all of their espresso machines. Okay, and if you think about this from Starbucks perspective, their espresso machines in their stores are mission critical devices. Okay, if all of imagine what it would look like if on a Monday morning every Starbucks espresso machine on the planet was being held ransomware. Okay, that would be definitely an economically devastating event for them. And I don't know, might even have societal impacts, people rioting in the streets over lack of coffee or things. Although that was a really funny joke, by the way, when I used to tell it back in 2019. It's not so funny in 2020 anymore. Okay, the world's changed so much, recognize that. But they wanted to be able to protect their espresso machines. And in fact, until they found Azure Sphere, they knew the value they'd be able to generate. They'd actually calculated what value they could generate if they had IoT, but they didn't connect the devices because they just couldn't find anything that was secure enough to allow them to connect those mission critical devices. So that they've used Azure Sphere and added it to their espresso machines. And the financial incentives are really quite simple for them. These espresso machines that are in all their Starbucks stores. So every Starbucks store has at least 2 of these espresso machines. And if the espresso machine is down, that costs them business. Okay. And so when an espresso machine's not working, the barista in the United States, they have an 800 number that the barista calls and says, help, our espresso machine's not working. And Starbucks sends a truck to fix that machine as fast as possible. Okay, and it costs hundreds of dollars to roll one of these trucks to go out and go fix the espresso machine. Okay, well, one of the things they found is that that the devices, the espresso machines, like over a quarter of the time when a truck goes out, the technician gets there and looks at the espresso machine and says, there is nothing wrong with the espresso machine. The baristas just forgot to clean the water filter out like they're supposed to do regularly, or they forgot to empty the grounds dispenser, things like that. So no technician needed. And so by having IoT on this device, when the barista calls the 800 number, says our espresso machine's not working, the 800 numbers, they've got a dashboard and they can pull up the data from that espresso machine and say, oh, you need to empty the water filter, or you need to flush the water filter, or you need to empty the grounds. And so the barista does that. It takes a couple of minutes. The machine's back online. They don't have to roll a truck, and it's back online. The barista is able to get back to serving customers much more rapidly. Customers are happy. Starbucks is happy because they didn't spend all this money to send a truck. And basically, for the cost of what they saved in 1 year on emergency truck rolls, they paid for their entire IoT deployment. Okay. And so the opportunities are just absolutely huge. Okay. But of course, the risks are there. And so that brings us to responsibility. And, my call to action is that, one, be aware, this IoT, I'm glad that we're working here in the IoT space, but more people need to be working in the IoT space. There's a lot of open questions and, challenges, and there's going to be more and more as we get to larger and larger IoT systems that are, hundreds or thousands of devices connecting in these big control loops with ML or stuff. There's a lot of opportunity there. But also, the other thing I'll say is I think we all have a responsibility. If you work for a company that's building devices, you have a responsibility to make sure they're highly secure. If you work for a company that is buying and deploying Azure IoT devices, you've got a responsibility to make sure that those devices really are secure. And and I will say, as a consumer, all of us are going to be buying IoT devices, and we really have a responsibility to make sure those devices are highly secure. And so, my call to action is let's secure the future. Let's help make, because we go into a fully digital world, let's help make it more secure. So with that, that's my presentation. I want to thank everybody who's listened in so far that didn't drop out on me. And we'll open up for, I guess, Nikhil, I'll turn to you and you'll manage questions, right?
That's right. Yeah. Thank you, Galen. That's great. We have plenty of time for questions. The protocol here is that if you have a question, you can either write it into the chat and I'll select questions from there, or you can raise your hand and I'll unmute you and you can ask your question. I'll start with a question that is on the chat already from Matthias Peyer. He asks, how do you perform secure updates of different components, such as, for example, the Bluetooth firmware or other components in a distributed and only partially connected manner? How is this done without user interaction?
Okay, so the base way we do update is when a device has access to the network, it goes out, it talks to the Azure Sphere security service, it attests and tells the security service which software it's running, and the security service, and proves, that it's not lying, that it actually has the software, and the security service then provides to our OS and to our daemon that's running on OS the new updates. Those get brought in, including the updates for like the firmware for peripherals that are hanging off the device, and we bring those into the device, and then and we'll hold them. And then we check with the app, is it okay? So for example, we don't want to do an upgrade in the middle of a dishwasher cycle, for example. We check with the app, are we ready? Is it okay for me to deploy this update? And once it's clear, then we update. And if the device gets rebooted, it'll then, it'll automatically apply those new updates. So it's scheduled. The other thing that I don't know what the other question is, and we do this for our kernel. We do it for the user land components as well.
Right. Great. Sai Venkatakrishnan asks, is there some intra-container security approach followed?
They're actually within the containers. The main thing we do within the containers is we're just providing the update for the software that runs inside the container. And what we encourage device manufacturers to do is to segregate their code by containers. So and one of the key ones of these is the real-time code has to run in a separate container because it has to run in the on the Cortex-M processors, the real-time cores, and those cores are not allowed to talk to the internet directly. And so we at least force a two-part container mechanism and give strong guidance that the real-time component should be built with the assumption that the higher level component is being compromised. And I'll give you an example like this. We had early on we talked to one device manufacturer who built gas stoves, and they had a gas stove that you could that they were adding connectivity before we talked to them, and when we got them. And they have discovered that you could remotely tell the gas stove to turn on the gas, and then an arbitrary point later, like days if you wanted, come in and tell the spark to go. Okay, so you've just turned a gas stove into an incendiary device, right? And so one of the things that, so for example, the real-time code that is controlling the actual igniter and is controlling the valve, that code should have time bounds on it, for example. So, and things like that. So we do that.
Actually, I wonder in that scenario, do you really even need to be able to turn on your gas stove remotely?
That is a really good question. I don't know the answer to that one. I think the scenario they were trying to enable is, you get up there, you have everything set up for dinner or whatever, and then you check it before you head home and tell, okay, go ahead and start warming up dinner. I don't know. Good question.
Right. A question from Mike Hicks, which also actually was on my mind. He asks, what is the role of security-oriented read type-safe programming languages and/or formal verification in the IoT space? And to that, I'll add, I'm wondering about your security monitor, and in level 1, and wondering how big it is, and if it could be analyzed using some formal tools.
Oh, that's a really good question. There's tremendous opportunity, right? I will say we do use formal verification of the of Pluton itself. So Pluton is formally verified that there are no side channel attacks side channel leakage, some things like that. And, of course, how to do formal verification in hardware is a lot easier problem than how do you do it on software. So I don't know how much can be done and what could be done. I'm sure there's more that can be done. And it's a great thing to have people explore. And right now, our Linux kernel is open source and it's probably too big for anybody to do formal verification of. But over time, our plan is to open source the lower pieces of the system and make it open. I'd love to see some people do some help us with verification of that stuff. So there's lots of opportunities. And on the type safe language, so one of the I'm a strong believer in type safe languages. This from our Singularity experience, for example. Of course, what we found with Singularity, one of the things we found is it's really hard with existing type-safe languages to apply them to a lot of code. It takes a lot of work. And so one of the things that I funded early on in Azure Sphere is the Check C effort that David Tarditi has led to build a variant of C that we can do type safety, particularly buffer overruns and a bunch of other stuff, and bring some of the bounds checking and things into. And I'll be honest, we haven't got I'll be candid. We have not gotten as far at using that inside Azure Sphere as I would like to yet. But I definitely think there's a lot of room there. We have people, for example, that are writing their Azure Sphere apps in Rust, for example. So lots of opportunity there.
Great. Yeah, I'd love to look at that security monitor at some point.
All right, deal.
Let me see. There's some more questions. Juan Caballero asks, did Starbucks update their espresso machines to support Azure Sphere or replace them with new ones? If updated, what kind of updates were needed?
Yeah. So that's a really good question, and it was actually it was a great experience when we so they have all these espresso machines, okay, and those espresso machines, I don't know what they cost, but it's somewhere in the $30,000 to $50,000 range per one of those espressos. So you imagine you start 2 espresso machines per store, 30,000 stores, $30,000 to $50,000 per, it would have been, I don't know, close to $1 billion. In that range to go replace every single one of those devices. And they wanted security as soon as they could. So what we ended up doing, you go back to, well, these are microcontrollers. They're really, really cheap. And so we built what we call a Guardian device. And it's a small box that has an Azure Sphere chip in it and the hardware necessary to plug into the espresso machine. And they basically bolt it onto the side of the espresso machine, so it's pulling the data out of the espresso machine and then connecting securely, through the security, using the security service to connect. And so it's what we call a brownfield deployment. And this Guardian pattern, we actually have lots of people that are using this pattern. Microsoft is actually the group at Microsoft that runs all of our data centers are using a similar kind of Guardian to connect all of the HVAC equipment in all of our data centers, because that's really mission critical equipment they never dared connect before. But when they found about it, Starbucks said, hey, they said, hey, could we repeat this pattern? So we have a lot of people doing that. Now, what Starbucks has done is we have this common pattern. We go and work with a company, help them get Guardians in place. And then they've gone to their manufacturers and said, hey, we're using these Guardians for right now. In the next version of your device, so the next wave that we buy, we want them to have Azure Sphere built in, and that's kind of the pattern. That's a very common pattern that we see.
Great. Julia, I think Julia Lawal asks, how customized is your Linux kernel? Do you keep it up to date with the latest kernel releases?
It's a good question. We are, as of our release, I think it was 2007, our release this summer, I think we're up on to the 5.4 Linux kernel. So we try to stay up to date. We try to push our changes. The customizations are not really deep. It's really kind of a lot more about how we build Linux. It's an incredibly flexible code base. And, we have some replacements that we've done for certain subsystems and then we build. It's more in the way we build. So it was I was actually kind of surprised at how easy it was for us to upgrade to the latest version when we did. Because before that, we were using a version, by the way, I don't remember the version number, but it was like like 2.5 years old. And the plan going forward is to stay very, very current.
Someone asks, will the threat model, or is it already, will the threat model for Azure Sphere be published publicly?
That's a good question. I don't think it's public. I mean, we kind of talk in kind of like these talks, kind of what, and in the best practices paper kind of talks a little bit about the threat model, but kind of in a kind of formally documented threat model. I don't think we've published it yet, and that's actually a great ask and probably something we ought to do. I definitely oppose. As a philosophy, our intent is to be very, very transparent. So, for example, when the security challenge we did this summer, we issued CVEs. Now, formal practices for issuing CVEs, as long as you are able to fix the issue so the customer never sees it or experiences it, you don't actually have to publish CVEs. But we felt it was important to, make our customers aware. So, for example, if they had a device that had been disconnected for a really long time, that it would experience a period of vulnerability before it got updated, for example. So we're trying to be very transparent. And like I said as well, my intent, our goal is to publish all of the sources for the OS ultimately, because more eyes on it is better than fewer.
Right. Actually, I wonder about your the program you had with McAfee and others, red teaming. Is that how does an average researcher get in on such a program?
That's a good question. So it turns out we actually have an ongoing secure bounty program. So anybody who wants to, they can get an Azure Sphere dev kit. They can download the sources from, get our Linux our Linux, our hub, our GitHub, our Git repo for Linux, and go to town if they want to. And hey, if you discover some vulnerabilities, there's a formal mechanism for how you report them to Microsoft. And so there's still bounties. This one we did. There's kind of baseline Microsoft bounties, and then we added up on top of that. And what we look for people who are interested in really helping us on the platform. So we do another one where we add these other bonuses. If somebody's out doing some work, publish some results, there's a lot more chance that they'll get into the bonus program, the extra bonus program.
I think a related question and a follow-up from Sai Venkatakrishnan is, I think he's wondering about, are there tools that Azure Sphere provides support for developers to code with good security principles? These are, I think, for app developers.
That's a good question. So we have a SDK. We actually have fantastic developer support in Visual Studio. One things that was very crucial to me as we built this. I've kind of always describe this is Microsoft and I assert Microsoft has two superpowers. One of them is security, and the other one is in developer tools. And so we brought all the power of Visual Studio and VS Code and to the platform. A great experience there. There is room for us to provide new tools and better tools around security coaching. Let me put it that way. It's good. We do have code to help them with building containers and doing the manifests and stuff like that. But I can imagine all sorts of ways that this community might come up with to help improve that.
Mike Hicks has a kind of a broad question, which is, he says, first we had security for multi-user mainframes, then we had security for PCs, then we had security for mobile devices, now we have security for IoT. Each step in this progression borrows heavily from what came before or fixes problems left on the table. It also adds something new. So, 1, what long-standing security problems are you fixing with Azure Sphere? 2, what things do you see as distinct in the IoT space?
Well, those are good questions. Well, I think one of the key distinctions to see in the IoT space is every previous generation of security has depended on humans in some way. And nothing else. Like there's an administrator for a device, for example. And in IoT devices, you don't have there's not a local administrator. Right. In fact, you really, when people think about devices, they don't want to think about an administrator, and that causes you to think about devices in a lot of different ways. And and also, and obviously, kind of raw numbers way to think about it. Those 9 billion new devices per year are going into a deployed populations of about 50 to 100 billion devices, just on base microcontroller devices that aren't IoT yet. So if all of those become connected, we're going to be way outnumbered by a factor of about 10 humans to machines. And, there's going to be new applications and everything else. So you imagine a world where, there's 100 IoT devices per human. We just can't do quite so human-centric as we have before. And so there's a lot of opportunities and some other things. One of the things that this led us to, for example, was this Pluton hardware-rooted trust. And I think the journey with Pluton's been really interesting because the Xbox devices are very much an IoT device. They're just, they've got different sets of sensors and actuators, okay, for how they interact with the physical environment. But, it's really fundamentally different than a PC in the way that it interacts with the user and what the model is and things. And we used that model when we created Azure Sphere, and we used Pluton from the Xbox. And now it's actually come full circle. Now it's interesting, that they've actually figured out Pluton and the capabilities that actually can be used up in the, in some of the preceding generations. We're now moving Pluton into PCs and realize that the benefits of, when you start thinking about, the human not being essential to the operation of the device, how do I take the human out of some of the critical loops, applies back in these other devices as well.
Yeah, I think that's really insightful. I like that.
Oh, good, because I made it up on the fly.
I'm wondering if Jim has a question. He keeps popping up on the focus, but maybe not. Surely you have a question, Jim.
So great talk. I'm a big fan of it, even though the one I have that you gave me is still sitting in a drawer someplace. But so I do have a question. So you were talking about singularity and safe languages and Dave's stuff. So how much easier would it have been to sort of build this using sort of better programming languages if you sort of had a clean slate approach, ignoring sort of the advantages of using the Linux kernel and all the development there? Would it have fundamentally changed the architecture? Would it have looked more like Singularity, or would you have kept? No, just curious. Would you have gone down this different path?
Yeah, that's a great question. I will say when the person brought that first chip to me and said, what operating system should we run on it? One of the things I did look at, could we create a very simplified version of Singularity, for example, that ran on that chip? And ultimately what I decided was that chip didn't have enough RAM and didn't have enough flash to be able to do, something quite like we'd done there. This is one of the, by the way, I didn't really talk about it much in this talk, but one of the changes we made to chips was not just adding Pluton, but also adding a processor with an MMU and some additional RAM and flash. And basically what we realized in 2015 is, turns out MCUs are on a Moore's law curve, just like every other type of processor. They're just like 5 generations behind, because when you build an MCU, you're building for the cheapest used depreciated fabs. Okay, but anyway, would have been easier. One of the things, okay, I think one of our negative experiences from Singularity was that every piece of code had to be rewritten to be brought into the system, right? And we think that about this embedded world, what we're looking at is all these embedded developers and how do we bring them into this and get them started? And, and you should think about, kind of my stereotype. It's obviously not entirely, like any stereotype, it's not really accurate. But kind of my stereotype for an embedded developer is this guy who learned how to program microcontrollers in the 1970s and is still doing it. Okay, in C, which is really these tight control loops. And so we kind of said, well, we're not going to pick them up and move them right away. It's more important that we figure out how to secure the environment around them than to move them. But I think, you know, there's lots of opportunity to change that and go forward. So I guess that's kind of my my base assumption. I will say, you know, we did have it was probably an okay venue for me to talk about this publicly. The initial version of the project, we actually ran NT. We took the NT kernel and we put it on top of the chips, and that took a very large number of person years in order to do that, to shrink it down and get it run in this environment. And then when we made the decision to move the Linux kernel, which by the way was Satya Nadella's idea, when we decided to use a Linux-based kernel, we had the whole thing up and running in 2 months on the clock and like 6 person months of effort. And you know, it's just an incredibly versatile, adaptable platform. And you know, it would have taken a lot longer to build a system from scratch. But one of the things we're trying to do is create a set of persistent compatibility interfaces in Azure Sphere that allow us to have a lot more flexibility to evolve our implementation over time, and while independently allowing the app developers to evolve forward or to stay on what they're doing. So, thanks, Jim. Good question.
There are lots more questions, and we still have some time. So if you're game, Galen, I can keep selecting questions.
Yeah, we can go to 10:30.
Yeah, okay. Matthias Payer asks again, the whole software stack is rather heavyweight for low-end IoT devices. How do you scale down to ARM, Cortex M0, or other SOCs without MMUs, i.e. if you can't run Linux?
Yeah, it's a good question. So one of the things, one thing I'll say is our Linux is a lot smaller than anybody else's Linux. You know, we actually run on devices with 4 megabytes of RAM and 16 megabytes of flash. Okay, so, and I say that because sometimes when people say, oh, you got a Linux kernel, they immediately say, oh, wow, that's super expensive, okay? The other thing I'll point out is one of the assumptions people make, you say, oh, we've got a Cortex-A. They say, oh, that's really expensive compared to a Cortex-M. And the way I'll say it turns out actually, if you take a Cortex-A and you set a clock that is more like a clock that you would have, a maximum clock speed that's more like you would have with Cortex-M, there's actually very little difference between a Cortex-M and a Cortex-A of a similar class. So like an A7 and M7, basically the exact same thing, very small delta from an M3 and M4. And most IoT devices have at least an M3 and M4. And really the way I'll describe it is most IoT devices, you know, once you start adding a network stack and start adding the security, you kind of push up what you're doing. There will still be Cortex-M class, M0 class devices. We don't address them with Azure Sphere right now. With our present solution, would it be possible to take a very similar architecture and create a Cortex-M solution? If you did the same changes we did in the hardware, I think there's quite a bit of possibility there as well. And particularly the Cherry work that ARM and that Cambridge is doing, I think offers some really interesting opportunities on those really, really small cores. Plus, I think it's also interesting in a lot of other places. So I guess there's my rough answer to that.
I think I'm picking a question from David, David Nauman, which also resonates with me. Trying to find the exact question. He says, apropos formal verification of the security monitor, are there specific difficulties beyond the usual?
Good question. Well, I'm definitely not a formal methods expert, right? I have no idea. I suspect it's actually because of the way resources are dealt with and things, I suspect it's amenable to existing technology for doing formal methods verification.
And can you give me a sense of if you can, how big is how many lines of code is it?
You know, I don't know how many lines of code it is. I don't even know how it's on the order of tens of K of code. Okay, you know, so right. So it's a pretty, you know, relatively pretty small code base.
Okay. I'm missing anything? I think the Sai Venkatakrishnan asks again. I think this probably is related to the question that Jim asked, and but I'll ask it, and maybe if you have any specific insight about this version of the question. What is the scope of bare metal unikernels without any hypervisors underneath on IoT devices, given the fact that some of these unikernels like Mirage use type-safe languages? That one uses OCaml in particular.
Yeah, it's a nerd's question. So if you did, okay, type-safe languages are really fantastic in that, you get buffer overrun protection and things like that, okay? But fundamentally, they're a single layer of defense, okay? So for example, they're very susceptible to clock glitching attacks. If someone can get the clock to be off or things, you're exposed. There's papers from back in the time we were doing Singularity of saying, that there's, if there's you flip a bit somewhere on one of those pointers, and all heck breaks loose, right? So they're, very much there's no defense in depth. It's a fantastic substrate. It's a fantastic for the layer it's at. It's a great thing, and we should definitely, every place that we can do type-safe languages, we should do type-safe languages, right? But you also got to remember, you need defense in depth, because when you've got billions of devices out there and some of them doing things that are, many of them doing things that could actually harm human beings, you don't want to count on just one layer of defense.
A couple of questions from YouTube. 35, 40 people watching on YouTube. One of them, I think, is a remark. It says, regarding CVEs, you should issue a CVE even if you fixed a bug before customers found out.
Yep. Yes.
Yep. And I think the same person asks, are there other security programs that you run except let me rephrase it. Other security programs that you run aside from the security challenge, and do you plan to run more things like that?
Yeah. Like in the broad sense of bringing in the research and doing it. It's an area where I not much, but definitely something that as we get a little more time and get a little more expertise, and the opposite, we get more kind of established with the platform, it's definitely an area that I'd like to see us expand in. So hopefully stay tuned.
Last two more questions. Jesu asked, as IoT.
Hey, by the way, can I say something?
Yes.
By the way, if anybody has any ideas for great security programs, things that we should do, I'm open. I left my contact information on the first slide. Happy to hear ideas from people from this community. Back to you, Nikhil. Question.
As IoT is becoming ubiquitous, I believe people will tend to manage them on their phones. Do you see any special security challenges on the mobile phone end, such as requiring some domain-specific chips for those IoT apps?
Yeah, good question. I actually don't know. Yeah, I don't know the answer to that one.
I would imagine that it's the phone controlling the IoT device. I mean, the phone remains untrusted. It's the device that matters.
Well, but if you kind of go back to the thing, am I using the phone to remotely turn on my gas stove? I probably really want to know that it's really the phone and that the phone hasn't been hacked, and and some things like that. So there's possibility. I guess here's the thing. I don't think there's anything phone specific is my first guess. I could be wrong. Okay. I'm wrong all the time, so I could be wrong here as well. I don't think there's anything phone specific, but there is this question: is as we move into a world where where more physical systems are accessible to more devices, how do we manage security in that? How do we do that? How do we establish trust and expand the protection domain out and have layers of defense and depth? I think there's a lot of open questions there.
Right. Time for one last question, if anyone has one. Otherwise, let's thank Galen. Oh, wait, here's one.
Last one.
Last one. Are most IoT devices single-use devices? Do they run a single application, or are there multi-tenancy challenges?
That's a really good question. Obviously, there are some devices that have multi-tenancy, but predominant, like 99.999% of IoT devices really are. Obviously, they're single authority devices, so they may have multiple apps, but the apps are all coming from like the OEM. The selection of the apps is chosen by the OEM, for example, and so but you want to have compartments to be able to protect the different pieces, so a failure in one doesn't propagate the other. But in general, opposite, what I talk about is we have embedded development and edge development. And embedded development, which is kind of the firmware level, that is single application or single authority. So, good question.
Great. Well, so lots of thanks pouring in, Galen. Thank you so much. That was I really enjoyed that, and really appreciate you making the time. Just wanted to remind others that this is the first in a series of talks. Our next one is on December 1st. It's going to be by Herbert Boss, and then we have a web security panel on December 2nd. So looking forward to seeing many of you back there, and spread the word. Tell your friends, and thank you all for joining in.
Thank you, everybody. Bye.
Bye.